Hey everyone, ready for another deep dive? Today we're tackling something that might just blow your mind. Slim attention. You know how frustrating it is when you're trying to run some crazy, powerful AI and just chugs along?
Ugh, yeah, tell me about it.
Well, slim attention could be the answer to our prayers. We've got a whole stack of research papers here, all about how this new technique can slash the memory needs of these massive language models.
Seriously, we're talking cutting the memory requirements in HackELF.
In HackALF, okay, you got to break that down for me. How is that even possible?
So traditional AI models use something called a KV cache to store all the information they need. Slim attention ditches half of that by calculating some of the data on the fly.
Hold on. So it's like they're figuring out what they need as they go instead of carrying around a whole library.
Exactly, and that translates to faster processing, longer chunks of text they can handle.
And maybe, just maybe, finally getting those powerful AIs running smoothly on our phone.
You got it. That's the dream, right?
You know, I'm seeing here that the research on this was done by Nils Graef from TBD Open Machine.
Yeah, he's a real whiz when it comes to making AI more efficient.
All right, so before we get too far ahead of ourselves, let's go back to basics for a sec. Remind me, how do these AI models usually work? Something about, what was it, transformer models?
Right, so transformer models are like the foundation for a lot of these large language models. They work by breaking down language into smaller chunks called tokens.
Okay, tokens, got it. And where does this KV cache thing come in?
Well, the KV cache is essentially the model's memory. It stores these pairs of keys and values that help the model understand the relationship between different words and phrases.
Keys and values. Sounds kind of like a treasure map.
Huh, sort of.
Yeah.
Think of the keys as labels and the values as the actual information tied to those labels.
So slim attention just tosses out the values and only keeps the keys. But doesn't it need that value information to, actually make sense of things?
It does, but that's the clever part. It calculates the values on the fly using a special formula based on the keys.
Okay, but wouldn't all that extra calculating slow things down? It seems like there's got to be a trade-off somewhere.
There is a bit of overhead, yeah, like taking a detour. But for long pieces of text, the time saved by not having to lug around all that data in the KV cache more than makes up for the detour.
So it's like, yeah, you might spend a bit more time calculating, but you're zooming past everyone stuck in traffic with their overloaded memory.
Exactly. And the longer the text, the bigger the advantage. They even tested this out on this model called Phi 3 Mini 128K, which is designed to handle huge amounts of data. Even for that thing, slim attention gave it a speed boost.
Wow, okay. I'm starting to see why this is such a big deal. It's not just about being more efficient. It's about making these AIs actually usable in the real world, right? Where you've got tons of info to process.
Exactly. And that's where the whole prompt phase and generate phase thing comes in.
Oh, yeah, right. Those phases. Remind me again how those work.
So the prompt phase is when you give the AI the initial input, like asking a question or giving it a topic. The generate phase is when it starts spitting out new text based on that prompt.
Gotcha. So how does slim attention change things up during those phases?
Well, during the prompt phase, everything's processed at the same time. Slim attention says, hold on, we don't need all those values right now. Let's just keep the keys.
Like pre-processing the information, making it easier to handle.
Yeah, exactly. Then during the generate phase, when the AI is creating text word by word, slim attention calculates the values as needed.
Smart. And I'm looking at these diagrams from the research paper, figures 2 and 3. They really show how much slimmer that memory footprint gets.
They do, don't they? Traditional AI models are stuck with this massive V cache, while slim attention just cruises along with its sleek K cache.
And there are two ways to calculate those values from the keys, right? Option 1 and option 2.
That's right. They both get rid of the bulky V cache, but option 2 is a bit more efficient during the generate phase.
Okay, cool. But you keep mentioning this term memory bound. What does that mean exactly? And what if my system isn't really limited by memory? What about all that extra calculation we talked about?
Good question. Memory bound basically means the system's speed is limited by how fast it can access data from memory, like trying to read a book where all the pages are stuck together.
So slim attention is like oiling those pages, making them flip smoothly.
Perfect analogy. Now, if your system isn't memory bound, meaning it can access data super fast, then yeah, you might notice the extra calculation from slim attention a bit more.
Is it like a deal breaker then?
Not necessarily. See, slim attention is pretty lightweight in terms of how much math it has to do. They even compared it to some popular computer chips like CPUs and GPUs, and even the most powerful ones were still more held back by memory speed than by slim attention's calculations.
So even on a super powerful system, the memory savings are still the biggest win.
Exactly. And it gets even better. Slim attention can get even smarter by taking advantage of something called sparsity.
Sparsity. Sounds intriguing. What's that all about?
Think about it. When you're reading a long article, do you pay attention to every single word?
Definitely not. I'm more of a skim and scan kind of reader.
Exactly. And it turns out AI models can do the same thing. They do a lot of calculations that aren't actually that important for understanding the overall meaning.
So they're wasting time and energy on stuff that doesn't really matter.
You got it. Sparsity basically means identifying those irrelevant bits and skipping over them, focusing only on the info that matters.
Okay, I see where you're going with this. Slim attention can be even more efficient by being picky about what it calculates.
Exactly. And while you can use this sparsity trick with traditional models, slim attention is already designed to reduce the amount of data it's working with, so it gets a head start in the efficiency game.
So it's like slim attention was born to be a lean, mean processing machine.
Ah, well said. And that focus on efficiency, getting the most out of your resources, that's what you're all about, right?
Absolutely. Now, I'm curious, does this slim attention play well with all the other fancy tricks people use with transformer models? You know, the AI world is constantly coming up with new bells and whistles.
That's a great question, and for the most part, yes. For example, it works with rotary positional embeddings, or ROPE for short.
ROE, right. That's for understanding the order of words in a sentence, isn't it?
Right on. Just like word order matters for us, it matters for AI models too. Slim attention has a couple of ways to work with ROPE, and one of them gets even more efficient when you use that sparsity trick we were talking about.
Layers upon layers of optimizations, like building this incredibly fine-tuned AI engine.
Exactly. And it doesn't stop there. Slim attention can even handle models with what are called non-square weight matrices.
Wait, non-square? I thought matrices were always square.
We usually see square ones, yeah. But some models use matrices with different dimensions for rows and columns, like a rectangle instead of a square.
Okay, I vaguely remember matrices from high school. But why does that matter for AI?
Well, slim attention can handle those non-square matrices too. There are a couple of ways to implement it, each with its own pluses and minuses, but the potential for memory savings is huge. There's this model called T511B that uses a really rectangular matrix, and slim attention could shrink its cache size by like 32 times.
32 times? That's insane, like going from a warehouse to a closet.
It really shows how flexible and powerful this technique is, and we've only scratched the surface.
Yeah.
There are encoder-decoder models that can also benefit from slim attention.
Encoder-decoder. Okay, those are new. Fill me in.
They're the brains behind things like speech recognition and machine translation, like Whisper, which transcribes audio to text. They have an encoder to process the input and a decoder to generate the output.
Got it. So how does slim attention fit in with these encoder-decoder models?
Same core idea, reduce memory without sacrificing accuracy, but these models have a cross-KV cache to help the encoder and decoder talk to each other. Slim attention can either shrink that or sometimes get rid of it completely.
Wow, what kind of real-world benefits does that lead to?
Well, one big one is faster time-to-first token. That's huge for real-time applications like speech transcription.
Okay, break that down for me. Time to first token.
It's the time it takes for the app to spit out the very first word of the transcription after you start speaking.
Got it. So no more annoying delay while you wait for the app to catch up.
Exactly. It makes the whole experience much smoother.
Definitely a game changer. Okay, so we've got a good handle on how slim attention works with encoder-decoder models generally. But what about something specific, like Whisper? How much difference would slim attention make there?
Well, lucky for us, the research paper goes into that in some detail, and the results are pretty exciting.
Give me the numbers. How much faster could slim attention make Whisper?
Let's look at the table here. It shows the potential cache size savings and speedups for all 5 Whisper models, using a standard encoder context length and a set number of output tokens.
I'm seeing some pretty impressive figures. Option 2, which eliminates the cross-KV cache, could make the total cache size 8.7 times smaller across all the Whisper models.
Yep. And what that means is a potential 5x speedup in token generation when you've got a batch size of 64.
5 times faster. That's insane. Imagine transcribing audio almost instantly with barely any lag at all.
It's a pretty amazing possibility. And it really shows the potential of slim attention to revolutionize how we use LLMs.
Okay, I am officially on board. This slim attention thing is sounding more and more like the future of AI. But before we get too carried away, let's take a quick break and come back to unpack some of the bigger implications of this technology. Sound good?
Sounds good to me. We've got a lot more ground to cover. It just highlights how slim attention could make these large language models much more accessible and way more practical for everyday use.
You know, it's funny. We hear about all these big AI breakthroughs, but they always feel kind of far away from our lives. But with slim attention, I can actually picture how it could change the way we use technology, even personally.
Oh, for sure. Imagine just talking to a super smart AI assistant on your phone, like a natural conversation, no lag or pauses or anything.
Or, like being able to transcribe a whole lecture in real time without even breaking a sweat. That would be amazing.
Totally. And the paper even talks about a hybrid approach, kind of mixing the best of both options to get even more fine-tuned optimization.
Hybrid approach. Ooh, tell me more about that.
So basically, it uses option one for one of the layers in the decoder stack. That's the one where it calculates and stores the cross-K cache. But then for all the other layers, it switches to a modified version of option two that uses the K cache from that first layer instead of the original encoder output. It's like building on the work that's already been done.
So kind of like a relay race.
Yeah.
Each layer passes on the optimized information to the next one.
Exactly. And while the savings from this hybrid approach might not be as huge compared to just using option two, it can still make a difference, especially for models with fewer layers.
Got it. So it's like another little control knob for fine-tuning how you use slim attention.
Exactly. And it's that control that makes it so exciting. It's not one size fits all. You can adapt it to different models and situations.
I'm really starting to see why you're so into this. It's not just about speed. It's about opening up all these new possibilities.
Exactly. Slim attention could totally change who has access to these powerful models. Imagine if anyone could run them on their own devices without needing a crazy expensive computer.
Wow, that would be incredible. It's really starting to feel like that vision is within reach now.
Totally. And as research in this area keeps going, who knows what other crazy memory-saving tricks they might discover.
Yeah, maybe this is just the beginning of a whole new wave of innovation in how we optimize LLMs.
It's definitely an exciting time to be following this stuff.
Okay, so we've gotten pretty deep into how slim attention works, the benefits, and even some of the possibilities for the future. But before we go too far, I want to circle back to something you said earlier about how slim attention is mathematically equivalent to the standard attention mechanism.
Right. You mean how slim attention doesn't cut corners or lose any information?
Exactly. It's not about doing things the easy way. It's about finding a smarter, more efficient way to do them.
That's such an important point. We're not talking about trading accuracy for speed or saving memory at the expense of the result. It's about actually improving the underlying algorithms to make them more efficient from the ground up.
So it's not just a clever hack. It's a fundamental improvement.
Precisely. And that's what sets it apart from other optimization techniques. We're not just trying to squeeze a little more performance out of the hardware. We're designing algorithms that are just plain better, regardless of the hardware.
That's a really cool distinction. It's like slim attention isn't just a temporary fix. It could be a whole new way of thinking about how we design LLMs.
Totally agree. And this focus on efficiency isn't just about being elegant, it's about sustainability too.
Oh, interesting. How so?
Think about the energy it takes to train and run these massive models. It's a big environmental concern. But slim attention, by needing less memory and computation, can make LLMs more energy efficient, smaller carbon footprint.
So slim attention isn't just about making LLMs faster and more accessible. It's also about making them more responsible.
Exactly. As AI gets more and more intertwined with our lives, we have to think about the impact on the environment.
Absolutely. Efficiency and sustainability have to go hand in hand.
And slim attention shows a promising way to achieve both of those.
Okay, you've convinced me. Slim attention is a total game changer. But, gotta ask, is it a magic bullet? Are there any downsides we should be aware of?
Well, like with any new technology, there are always caveats. I mean, slim attention is still pretty new. It needs to be tested more rigorously across more LLMs and real-world applications.
So we need more data before we know for sure how effective it'll be in the long run.
Exactly. And another thing to remember is, as we talked about, slim attention does involve some trade-offs. Yes, it can drastically reduce memory usage, but it does add a little bit of computational overhead.
Right, that extra step of calculating the V projections as you go.
Yep. And even though this overhead is often more than made up for by the memory savings, especially when you're dealing with long chunks of text, it's something to consider when you're looking at the overall performance.
So it's not going to magically make every single LLM faster and more efficient.
That's right. It's a powerful tool, but you got to use it the right way.
Okay, that's fair. But even with those caveats, slim attention seems like a huge step forward.
Totally agree. And I think it has the potential to spark a whole wave of new ideas for optimizing LLMs. Who knows what other crazy memory-saving techniques people might come up with down the road.
The future's full of possibilities. But one thing's for sure, slim attention is definitely making us rethink how we can make these powerful LLMs more efficient and accessible. And sustainable, too. And that's awesome.
Couldn't said it better myself. It really shows how creative the AI research community is, and it's a great reminder that even the most complicated systems can be made way more efficient.
So to sum it all up, slim attention, faster processing, longer contexts, better use of resources, it's like the ultimate upgrade for LLMs.
And what's really remarkable is that it does all of that without losing any accuracy. It's a win-win all around.
And it's not just about researchers and developers either. Think about how this could change things for regular users.
Yeah, if you zoom out and look at the bigger picture, slim attention could be the key to finally being able to run these powerful LLMs on our phones and tablets. Imagine having the latest AI models right in your pocket, no need for a supercomputer.
Whoa, that would be a game changer. No more relying on the cloud or settling for limited offline models. We can have truly intelligent assistants right at our fingertips.
And that's just the beginning. Think about what it could do for real-time translation, personalized education, even creative writing. The possibilities are truly endless.
So while slim attention is still pretty new, it's got a seriously bright future.
And that brings us to a really interesting question for everyone listening. What are you going to do with the power of slim attention? How are you going to use this breakthrough to unlock new possibilities in your work, your research, even just in your everyday life?
That's something to think about for sure. We've given you the knowledge, the tools, the inspiration. Now it's your turn to get out there and explore what you can do with slim attention.
Who knows? Maybe your discoveries will end up being the focus of our next deep dive. But until then, keep asking questions, keep exploring, and keep pushing the limits of what's possible.
And that brings us to the end of our deep dive into slim attention. We hope you've enjoyed exploring this amazing new technology with us. See you next time.